The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, welcome to our introductory session. I hope everyone is able to hear me. This is session 1 of our 11-part course for Big Data and Hadoop. My name is Anjana and I'm part of the team here at Know Big Data. I will take a few minutes of your time to take you through what to expect of this session and to introduce you to Know Big Data. Please make use of this time to send in a quick one-liner introducing yourselves. So the session is going to be about 3 hours long. The first half will focus on what big data is and why it is relevant in today's world. And the second half on Hadoop architecture. There will be a 10-minute break about an hour and a half into the session. That is at 10 p.m. IST. Please use the chat window or Q&A window to introduce yourselves and for any queries that you may have. For this session, this will be a primary mode of communication with the instructor. Since this is an introductory session, we keep this open to people and have a lot of attendees, which is why everyone is muted. So our instructor will read out the question before answering it and will do his best to answer all the queries that are posed. You can help the instructor respond to more queries and comments by keeping your messages short and avoiding chat language. For those who will be joining us for the rest of the course from tomorrow, the next session will have fewer attendees and we will be using a different tool which will be more interactive. For those making notes, please sit back and relax. We will mail this presentation and recording to everyone. So before introducing you to Big Data and Hadoop, let me introduce you to Know Big Data. Our primary focus is online trainings relating to big data and data sciences. We are thrilled to provide our course takers with instructors who are industry experts. You will soon find out for yourselves how true that is during this session. As part of the course, we provide access to Cloud Labs, which is a cluster that you can use to play around with whatever you learn during the classes. This feature is unique to Know Big Data and gives you a real feel of how things work at organizations that use big data. This is a feature that we are extremely proud of because we are pioneers in this particular feature. Course takers are also given lifetime access to our learning management system, which will include all the presentations, recordings, assignments, and project work. You will be able to use the aforementioned Cloud Labs to complete a real-life project, at the end of which you will receive a certificate, which can be shared on social media if you wish, like on LinkedIn, Twitter, Facebook, etc. You will also be part of our alumni group. We like to refer to it as Knows Big Data, which will keep you posted of new job opportunities, help you stay updated and connected. So let us move on to today's session. Our instructor today is Sandeep Giri. I will let him introduce himself and take it over from here. Have a great session.
All right, everyone. I'm Sandeep Giri. Are you able to hear me? All right. So my voice is clear. Great. Great. Now, okay. So Megha is not able to hear. Anjana, could you help Megha? All right. Great. So let me give a quick introduction about myself. I did my graduation from Roorkee. Then I worked in a company called D. Shaw for 3.5 years. So D. Shaw, we actually worked on big data systems in 2002. We had a 10,000 node cluster, and probably D. Shaw was one of the pioneer in the big data world, which is unsung company. Nobody knows about it, but Dsha does a lot of data churning for doing a lot of financial analysis. Okay, it's a world's biggest arbitrage company. So there we actually did a lot of things similar to what we talk about today in Apache Spark and other things. Now, afterwards, I built a company called Tbits Global, where we built a product called Document Management System for for building the power plants. Right? It's being used by big companies like L&T Power and Tata Power and Tata Projects. So afterwards, I joined Amazon and InMobi, where I worked exclusively on big data systems and working on various kinds of product. So at InMobi, for example, I built a recommender churning 200 terabyte, and Amazon I built tools similar to what we know as Apache Spark. And then in 2014, I founded No Big Data. I co-founded No Big Data with other people. Right? Now, so that was about me. Let me read out a little bit about you guys also, so that everybody knows that what kind of audience we have today. All right. All right. So first of all, no need to worry about taking notes. The presentation will be sent to all of you, as well as this recording will be made available to you, all of you, even if you are not signing up for the full course. So there are most of the attendees are those who are our students who have taken up this full course, and there are few people who have come to take the demo session. All right. Now, so we'll be sending you this presentation and the video. So we have Megha, Avinash, Sushant, Ashutosh. Yes. So Julie, yes, it is the first class of the 11 sessions. Out of 11 sessions, this is the first session. All right. All right. We have Seema, we have Ashutosh. Ashutosh works on a cloud. And all right, let me do a quick introduction right now because I'm not able to share the questions with all of you. All right. So we have Ranjit from Thomson Reuters. That's great. And Sharan is a business development executive. Good, good. So this session would be useful to you. Okay, in case, and you will realize whether to go ahead with the rest of the sessions or not. Avinash is a web developer, great, and all right, and Srinivas is here. All right. So Sushant, yes, I'm going to start from the basics, actually very basics, starting with questioning why do we need all of this now? All right. Avinash is an application developer, and Avinash is from Mindtree. Great, great to know you, Avinash. And Seema has been working on relational databases. Great, that is good. Arun is a co-founder of Affiliate Consulting Services. That's great. Great to have you, Arun. Okay. Julie is a government contractor and is a software developer. That's great, Julie. And Julie is from US, and so is Megha. Megha is a bioinformatician. That is great. That is great. I look forward to see how can we contribute towards bioinformatics, and would like to have further discussion with Megha. Now we have Sushant, who is a data analyst. Great. And yes, Ashutosh, all the other 11 sessions are going to be on GoToMeeting. There is another tool similar to this one where you can see the chats of each other. That is what we are going to use for rest of the sessions. All right. Okay. Hi, Nakul. Nakul is still doing his engineering. Great to have you here. Hi, Anamitra. Yes, Avinash, you should be able to build a career in Hadoop, and I'll discuss that. Okay. So, yeah, Ankit is working at Infosys. Good, good. You have started to look out for this kind of a course. This is great. And nobody's mic is working right now. All right, except for myself. All right. Avinash doesn't know Java. Don't worry. In case you have done any programming earlier, you should be comfortable with this course. Okay. Devik is a software developer, embedded systems. That is great. Great to know, Devik. All right. So Anamitra, just hold on for some time for your question. Your question is very valuable. And in case I miss to answer you, remind me in the second half. This is a very important question. Okay, okay, good, good. So Devik has read a book on big data by Victor Mayer and was interested to learn more. Great. Okay, Anupma Nagraj from HP and working as senior technology consultant. Great to know you, Nagraj. Himanshu is also from second year. So yeah, so actually all the people, most of the people who are attending this course, they are from a background where they don't know much about big data so far, and that the technology stack is fairly new. The whole Hadoop became popular in 2011. That's hardly 3 years. Okay, so lots of people are fairly new in this domain, so nothing to worry. Prasad is with Accenture and is a test automation architect. That's great, Prasad, and you have chosen a right path. And we have Vidya. All right. So Vidya's question is, most of the companies ask for project experience. So how do we make a career change to work in big data space? So not all companies ask for project experience. All right. Therefore, a lot of companies also ask for a online questionnaire. Like our one of our knowledge partners, they don't really ask for project experience, and In case you are interested, in case you really go through our session with the complete attention and you want to go for a long-term project with us, we will be more than happy to work with you. And that way you will get a 3 months working certificate, provided you really work with us. We'll provide you a stipend for those 3 months, as well as we'll provide you a real-time project. But for that, we will do an evaluation after the session, whether it is worth going with you as a 3 months internship. We'll do a separate evaluation after the session. All right. So that may be of help to you. Now, okay, then these were introductions. So again, let me iterate with the prerequisites for this course. Prerequisites for this course is you should be informed about what are databases. Okay. What are databases? As in, how do you manage the data in today's time? So the answer is using SQL and relational databases. So you should know basics of it. How do you put the data? How do you take out the data? How do you prepare how do you query the data? That you should know that. And second thing you should know for this course is any programming language, you should be comfortable in the basics of, say, what is a for loop, what's a variable assignment, what is a function. So those kind of things you should be okay with. Okay. And rest of the things will fall into place automatically. The third thing which I request everybody to do is just go through the basics of Linux. You should be comfortable at the command line, operating at the command line, because most of these tools do not have a UI. Okay. All the 13 tools which we are going to discuss not all have a UI. Therefore, you should be comfortable with operating from command prompt. All right. So great. So we have a great set of audience today, and I'm getting a brilliant questions right away. So Megha, are you able to hear now? I guess not. Okay. All right. All right. So regarding book suggestions, book any tutorial will do, any basics of Linux tutorials will do. Now, so okay, so out of 11 sessions, today we are going to discuss the first session, understanding big data and Hadoop architecture. All right. Now, before I jump into the whole session, let me quiz you a little bit. Answer my question by using the chat window. All right. So, what exactly do you understand by big data? So, whatever you understand so far, whatever you have heard so far, just try to say that. So, Megha's answer is large database. Himanshu says collection of data in huge amount. And Gina Reddy says that huge data. Ashutosh says unstructured data. Dealing with huge amount of data and processing it. Large amount of data in tera or petabytes. That was Arun. Before that was Seema. Any kind of data is Himanshu. And data that is huge and cannot be processed by DBMS. That's Vidya. That is good. Large database distributed over many servers or systems. That was Ankit Panda. Jaws says data arriving from all possible options. Okay, all possible options. Good. Arun is structured and unstructured data. Anamitra says huge amount of data that could be in any form, raw or other format. All right. Ashutosh says it is the 3V definition. Avinash says large amount of data which is not organized. Julie says allows more relationships in data than regular database. Okay. If you can't process, handle it in reasonable time on a single machines, and your methods need to explicitly worry about how to scale to handle the data volume, it is probably is big data. That was Abhinav. That is probably the best definition I have got so far. Ashutosh says volume, velocity, variety. And Ashutosh, why not veracity and other V's? Shwara says extremely large dataset that can be analyzed computationally to reveal pattern trends and all the analysis. Devik says large data from different areas used to arrive intelligent decisions. Good. Ranjit also says distributed and large amount of data. And Himanshu says extremely large data sets that may be analyzed compared to reveal patterns. Okay. Anupma, large data set in recent time drive to big data. Good. So yes. So some of you have driven the definition really well. And all right. Good. So no, actually everybody is able to hear Abhishek. All right. So good, good. So most of you have been able to answer it, but some of you had an incomplete definition. Now let me focus on my definition. Okay. So what exactly is big data? In very, very simple words, big data is data of very big size that you cannot process with usual tools, usual databases, and you require inevitably a distributed architecture to solve this kind of problem. All right. Data could be in any form, structured or unstructured. So here, the most important aspect of the question is what is big data is the distributed architecture, because saying data of very big size does not make sense. How big, you might ask, right? So my answer is going to be so big a data that you can't handle on one machine and you require a distributed architecture. We call it a big data, right? So that is what it is. All right. Now we have other aspects also, structured and unstructured. Okay. So data can be either structured or unstructured. We are only saying any kind of data. Okay. So fourth point is also meaningless. The second point also does not make much of a sense here because we are saying usual tools. What do we mean by usual tools? Therefore, the point number three, distributed architecture needed, is something you should always keep an eye on. Okay, so whenever you are classifying a problem as big data problem, or you are classifying a data as big data, you should keep in mind that to process or handle it, if you require distributed architecture, you should say that we have big data. All right. So this is the thumb rule. This is the thumb rule how you measure it. Although although there could be hundreds and thousands of definition, and we could have a debate for lifelong saying this is big data and this is not big data. But as a thumb rule, whenever you require a distributed architecture to handle and solve your problem, you can say that this is big data. All right. Now, but sometimes when people ask you during discussions, interviews or something, you might have to do a little stereotype answer. And this is the stereotype answer. This was given by IBM, which says that basically these are the characteristics of data. Okay, that might make a data big data. And what are those characteristics? It could be volume, it could be velocity, it could be variety, it could be veracity. All right. So if you have, so I will just take one example of each of these cases that should be sufficient. So first one is volume. Volume means you have got humongous data to store. Say say every time there is a Boeing flight 737 goes, you get 240 terabytes of data to store. And this keeps on happening every day, right? Or every once in 2 days. So here, when you have the volume, you need to worry about storage. And if you are unable to store the data using a single machine, that means you have got big data. Big data by virtue of volume. That is what is big data. That is what the characteristic called volume. Now, second characteristic is velocity. Now, velocity could be really fast. Velocity means that the data is in motion. Data is in motion. And when will this data be in motion? When will this data motion will become your problem? Examples are building a real time bidding system, or building a analytics, say web analytics. So for example, Google Analytics is getting so many hits from all around the world. Almost every websites use uh, analytics like Google Analytics. And every time you visit the web anybody's website, a hit goes to Google server, which means all the people who are browsing the website which have embedded Google Analytics is going to hit Google servers. So here there will be lot many requests coming in per second. Although although you might be sending a very minuscule data, as well as Google might be sending very minuscule data back to you. So the volume is quite low, and still there is a humongous traffic. Okay. Or let's say you have built a website counter which just similar to Google Analytics, but just takes account of how many hits have been there. At the end of day, you have only a single number which has increased. So the volume is almost zero, but velocity is huge. Lots of people hitting your website. So in such cases, this is velocity. And if due to this velocity, you might end up having a newer architecture and having multiple servers to cater to users, you say that, hey, I'm dealing with big data. And why? Because we have got humongous velocity. All right. Now, there is something called velocity. And so sometimes, even though you do not have volume or velocity, there could be there could be a need of distributed architecture. Distributed architecture means using multiple computers to solve your problem. All right. Because of the variety of the data. Take a case of variety, as in the data could be in a very complex structure. There could be relations, there could be the format problems, there could be difficult to decrypt the data. So there could be hundreds of situations. Okay. Or there could be a decompression compression involved while reading the data. So there could be lot of kind of formats of the data, because of which you might end up using a distributed architecture. And variety, take a case of Google Maps, or take a case of maps. When you are building something like a Google Maps, which is basically telling you location, I mean telling you the way from one point to another, and is considering traffic. Okay, all right. So let me just turn off my phone. All right. Now, so variety. I was talking about variety, where say you have Google Maps, where you have to find the path from one location to another, and say imagine that a country like India would be having hardly 100 GB of data, 100 GB of maps data, and if you have to find path from one location to another, there is no velocity involved, so volume is hardly 200 GB. There is no data is not increasing rapidly, but still the problem is very very complex, and you would require a distributed computing to solve your path finding problem in a reasonable time, right? So that's an example of why variety makes up for big data problem. Okay, now fourth problem is really really strange, but it's like a derivative of other problems. Now, all right, so veracity means data in doubt. Okay, now imagine this: you got five different data sets of temperature data across the globe. Okay, where temperature data is has basically the location and the date and the temperature in degree centigrade or whatever form. Now you have got various kinds of formats of data. First one is based on lat long. Okay, latitude longitude, gps, from using gps coordinates. Second data set you have is based on zip code. Third data set, the data set you have is based on your third data set you have is based on city wise. All right, so you have got these 3 to 4 data sets. Now till the point you conclude that this data is what is useful to me and these data are useless, you are going to handle and analyze all the three data sets. All the three data sets you are going to analyze, and therefore just because of the doubt, we have three data sets which might be so huge that you might have to use a distributed computing. All right, so this is the standard definition, and it is good to stick to this definition. Okay, but when you are going to take a decision about whether your problem is a big data problem or not, you are going to use the first definition. All right. So now another simple question to quiz you: how many bytes are there in a petabyte? How many bytes do you think are there in petabyte? All right. So let me repeat my answer for Avinash. Avinash says that what is veracity? I didn't get it. So basically, due to confusion, or the confusion could be whether to keep dataset A, B, C, or whatever. Till the point we realize that which dataset is useless, which dataset we want to keep. Till that point, we might have to retain all the kind of dataset, because of which we have duplicity of data and hence the volume of the data. So, so because of this confusion or inconsistency, we have to handle huge data, and therefore we might end up having big data. Okay, if you have 10 times of the actual data, that makes up for the case of big data. All right, so good. How many bytes are there in petabyte? 10 to the power 15. Good. Okay, so a petabyte, Ashutosh says 1000 terabytes. All right, Good, good, good. So the quick answer to the question is 10 to the power 15 zeros. Okay, and that should be good enough to do your back of the envelope calculation when you decide. So whenever we deal with any of the big data problem, we need to first analyze what kind of data are we dealing with. We cannot stay the way we have always been agnostic about the size of the data. When we write our queries, we were more focused on business logic. We were not many much focused on architecture. We always assumed that our database is going to handle it. But when you deal with big data, there is no way other than being able to uh, uh, no way other than understanding the kind of data you are going to deal. So, and to do that, you will have to do a lot of back of the envelope calculation. All right, and for that you need to have these petabyte terabytes in like uh, you should be able to recall them very easily. All right, so easiest way is kilo mega giga terapeta, and each of them is a 1024 of the previous one. All right, so yes, and a byte is basically 8 bit, and it can store 256 states. Okay, one bit can store two two states, 2 bits can store 4 states, and 3 bits can store 8 bits. 3 bits can store 8 states, and so on. Okay, all right. Now we know what is big data, and we know what is petabyte. So based on your understanding of current IT architectures, or current your expectation from current database systems, can you tell me that is 1 petabyte data is big data? Is 1 petabyte can you call big data easily? Sushant says yes. Siva says no. Exabytes is big data. All right. Vidya says yes. Ashutosh says no. Ranjit says yes. Avinash says yes. Seema says yes. Himanshu says yes. Ashu says no. Maybe. Julie yes. Devik yes. Nakul yes. Megha says no. Not sure. All right. So Arun says depends. Yeah. So I want to ask you, Anamitra, that what is the criteria? So we talked about big data. Big data means if you require a distributed architecture for your problem, then it's a big data. Now, 1 petabyte has got so many zeros. Now, my question to you is, what is the minimum thing you are supposed to do with the data? The minimum thing you are supposed to do with the data is being able to store, right? The minimum thing. Now, my question to you is, can you store 1 petabyte data reliably on a single machine, or using one of those network file system kind of architecture? Given the current state, can you handle, can you manage peacefully 1 petabyte of data? Just the storage part. We'll talk about processing later. Right. So most of the machines cannot handle none of the machines actually, it's in my personal experience, can actually connect 100 thousand 1 terabyte hard disks. All right. Good, good. So now, so everybody is now convinced that yes, 1 petabyte is a big data. All right, because most of the systems cannot right away start storing 1 petabyte data, and most of us who are saying, some of us would be saying that hey, we can store it in network file system. We will question that belief also in a minute. All right, now. Why big data? This is a classic graph which shows that some of the companies keep on doing this. Some of the companies keep on doing this kind of a study, that how many hard disks are being sold, what is the, so based on how many hard disks are being sold, they are trying to track down what is the, how is the digital storage expanding. So here is a sudden growth of data. Sudden growth as in exponential growth. In 2002, suddenly the data started growing. The gray section in the below, that is digital, while analog is continuously shrinking. Analog is paper, film, audio tape, and analog tapes and vinyl. All of those fall under analog. Now, this analog storage is essentially something like a very, not many people are storing data that side. Most of the people are have moved to digital storage, and 2002 was some point where the data started exploding exponentially. And why did it happen that way? Why did it happen that 2002 we started calling the beginning of digital era? Now, the simple answer is smartphones, or you can say devices and connectivity. In very simple words, the answer is devices and connectivity. Devices means devices means the your various kinds of devices at various monitoring level, and most important of them is your mobile phone. All of these devices, including mobile phone, tablet, laptop, everybody, all the hardware devices, they all had a single agenda: cheaper, faster, and smaller devices. And the miracle started happening since the time uh, uh, there has been lot of innovations in the electronics domain. So the smartphone became so accessible and cheaper. As of today, uh, I mean, everybody can afford a smartphone. Almost everybody. Now, second thing which led to the explosion of data was connectivity. As of today, everybody is almost connected, right? So while on one hand devices like smartphone generate the data, connectivity multiplies it. And that's what the leads to the big data. Connectivity multiplies it, while devices generate the data, capture and generate. Now, to make it accessible to the user, there are lots of softwares like Facebook, YouTube. They also assist in, they put all of this, the devices and the connectivity to the use. All right. Now, so, so I hope everybody is convinced about the fact that why we are talking about this now. Because, say, for example, today we are talking here, I'm giving a session. The effective amount of video I'm generating is 1 GB. In 3 hours, it will be one gigabyte. And at the end of session, this 1 GB would be transferred to all of you, okay, parallelly. So there are 30 people in the session, which means there is a total transfer of 30 plus 31 gigabyte. 1 GB from me to GoToMeeting servers, and 30 GB from GoToMeeting to you. So total amount of data transfer would be 31 GB. Now, if you see this, connectivity multiplied it by 30. Okay, while having a device with all of this functionality generated only 1 GB. So in the similar fashion, the data is being generated parallelly. So Himanshu, which point do you want me to explain again? Right? So I was explaining that while the devices capture and record the data, there are many sensors in your phone. They have a vibration sensor, they have a GPS sensor, and there are camera, there's a gyro sensor which detects the directions, and there's a magnet in that which direct direction, I mean horizontal direction, while gyro detect your vertical direction, and so on. So lot of sensors, lot of these devices, the internet of things you call it, they keep on capturing the data, and connectivity makes it multiplies it, makes it available at various other places. As and social, the softwares, Facebook, YouTube, Twitter, Google, and all the analytics engine people have built, they put the data to use into perspective, and therefore all these three things combined has led to a lot of data explosion. Till the time people did not till that point when people did not realize that they could use the data to generate lot of insights, people were charging a lot for even emails. Since the time Google figured out that hey, using Gmail we can do a lot of interesting stuff, so they started giving Gmail for free, right? So similarly the software has motivated all of these devices and smartphones to capture a lot of data. All right, now why does handling of big data become a problem on single machine? That is very important to understand. So there are four things in your computer which lead to the processing of data. First, CPU, where CPU reads the instructions from the memory and executes them one by one. Okay. So faster the number of instructions your CPU can handle per second. Instruction can be as simple as go to this particular instruction, read it and execute it. And there are other kinds of instructions also that turn on this voltage at this particular pin. So that's what CPU does. Now the CPU, the faster the CPU, the number of instructions it can process per second, the faster it is going to work for you. But CPU alone is not a problem. CPU alone is not a problem. Most of the time, CPU is good enough, but there are other factors which are stopping the CPU from working. The second one is memory. There are chances that the memory is either you are not able to put all the data into memory which CPU can process, or your RAM is slower. So if the RAM is slower, no matter how fast your CPU is, you cannot go beyond a particular speed. Or the the data bus which connects CPU to the RAM, if that is slow, then even though your CPU might be very fast, but you cannot do much, right? Now third thing is disk. If you have got huge disk on the same machine, you can store huge data. But if your disk is not sufficient, you might have to move the data to the network, and then network will become your one of the pieces of puzzle which would matter to you. All right. So when you are designing a software, you are basically juggling with these four aspects. All right, these four aspects. So So to solve a problem at any point of time, you basically have these four measurable component. Now, any of these component will become your bottleneck when you are handling big data. Any of these four components of your computer is going to become the bottleneck when you handle the big data, right? Let's take a case. First, you started with some churning of data, and you realize that we are not able to fit it into the RAM, so we've kept it on the disk. Now your disk will become the bottleneck because you have to read the data from the disk and then try to process it. Now if the data grows further, keeps on growing further, you cannot store it on the disk, you have to move it to the network. to another computer, and then you access the data using a network, and then your network will become the bottleneck. So you will keep on shifting these bottlenecks from one place to another. All right. And basically, when you are dealing with big data, y- or any of these four puzzles will become the bottleneck, and then you will require a network architecture or distributed architecture to solve it. So most of us are able to are convinced that, hey, if we have multiple computers, multiple CPU, will have benefit. If we have multiple RAM, definitely benefit. If we have a disk, good. But having dual network, how does it solve the problem? The answer is, instead of bringing data to the network, if the network is becoming the bottleneck, how do we solve the problem? So the thumb rule which most of these tools follow in when dealing with big data is, instead of taking the data to the computing, taking the data to the program, the way we had, you remember those older software? You write a query, that query brings data from remote, then queries it, then processor puts the data back into the database. Now, rather than bringing the data from server to here, we take the code to the server and process the data over there and only bring the results over here. So that's how we solve the network bandwidth. All of these four problems distributed computing tries to solve. Okay. So whenever we are using distributed computing, it's not that by using two computers, your answer will become 2x time faster. It might become far more faster than that, because all these four components will become doubled. So what does it mean by bottleneck? Bottleneck means the one which becomes the constraint. As in, if there are if there are three people in a team and they are working in a chain, I give something to you, you give you pass it on further. If you are slow, all of these, the whole process becomes slow, which means you are the bottleneck. Okay. So let's say me, you, and somebody else are standing in the queue. I hand over a brick to you, and you hand over the brick to somebody, the third person. Now, in case you are slower than both of us, you are the bottleneck, because no matter how fast I am, no matter how many bricks I can give to you per second, you are still going to you will not be able to handle it. Therefore, I'll have to wait, and the person who is in front of you, to who you are handing over the brick, will also have to wait, and hence you are the bottleneck. So that is the meaning of the bottleneck. Yes, Gyanendra, go ahead, type it. All right. Now I'm moving ahead. Now there are few example customers of big data. Okay. First one is e-commerce. In e-commerce, I'll take a few examples, and rest I'll leave it up to you. First and most prominent use case of using big data is recommendation engine. That was probably one most useful case, which came from companies like Amazon. So if you visit amazon.com, and just below the product detail, when you click on a product detail, you will see that people who visited this page also visited these pages. You may also like these. Those are called recommendations. Now, why does big data matter to recommendation? The answer is twofold. First, big data means better recommendation. Big data means better recommendation. All right. Now, If we had to generate recommendations earlier, we would actually truncate some data because we were not able to process it and generate the recommendation. But if you truncate the data, if you try to trim the data, your answers, your recommendations will not be very great. Okay, so that is why big data leads to better recommendation. More the data, better the recommendation. Okay, so let's take this case. I and there is one more person in a room. We are sitting here and discussing movies. I ask him, "What are your favorite movies?" And he says that he likes Matrix, he likes Casablanca, he likes other movies. And then I tell him about my movies. And then he says, "Oh, we are similar, quite similar to each other. And you may also like these movies." And I give him the recommendation, "You may also like these." Now, this is two people discussing movies. First, we have very small data set, meaning we'll have very small number of recommendations. Second, we may be absolutely wrong. Maybe it so happened that we liked two movies, but there are high chances that our behavior is very different and we may not be liking other movies. So if you had more people in the room and you had bigger history about their movie preferences, you will be able to get a very closer match to one person who is similar to them. Okay, and hence a better set of recommendation. So the more people have, so what I'm trying to say is clustering will be more meaningful if you have very huge data. Why? Because the the anomalous behavior or the aberration in few people or will get overlooked by humongous data or a mistake in some of the form of data. Therefore, big data is best use case for big data started with the recommendation engine. All right. So let me have a look at the question. What is the difference between recommendation engine and ad targeting? Okay, I'll talk about it. Although they might look very, very close, and for ad targeting, you might be using recommendation engine internally. All right. Now, then there is something called now there is something called search quality. All right. So whenever, even though you are building a very small in-house search engine, the expectation of people from your search engine are quite high. Okay, take a case of document management system which we built. From our calculation, we were my plan was that we will have hardly 1 terabyte of data after 5 to 10 years for one customer. Now 1 terabyte is not a big deal, but question is, even for this kind of a smaller data, say 1 terabyte data, 1 terabyte is actually huge if you think about relational databases. The older times, like 2005 times, year 2005, 1 terabyte is a huge data. But question is, even though you have to provide search in smaller data, the expectation from your system is quite high, and how are you going to match that expectation? People have used very advanced systems now. Whenever they try to find something in Gmail, they are able to find it, and whatnot. Now, search quality is inevitable even though you are building a small system. Search quality in terms of various parameters. First, providing a search in various kinds of inputs, such as your files would be images, videos, and hundreds of such format. You might have to provide search in all of those, and you might have to extract text from each and every file. That would be very, very time consuming. So you might have to distribute that process of text extraction. Second, you might have to build very custom dictionaries which suit your user behavior. Meaning, say your users are trying to search for Blue Dart, which is a courier company, which they send couriers. Now, Blue Dart could be written in hundreds of ways. Now, how would you build how would you build a system which automatically gives a recommendation to the user? Did you mean this? This can only be done if you build dictionaries, and these dictionaries you will have to crawl the web and churn a humongous data, and therefore even a simple search problem become a big data problem. Now, all right. Now, third aspect is sentiment analysis. Your company might be very small, but the sentiment which you can gather about your product, the things you follow could be huge. The sentiment could be huge. As in, say, for example, you are somebody who is building some small product. Now, as soon as you launch a product, you might have to query Twitter and figure out what are people talking about. Okay. Secondly, before you build something, you might want to do a little bit of analysis, and sentiment analysis is one of the cases you might look forward to. Now, what is sentiment analysis? Understanding the sentiment of people over a period of time with respect to a particular product or a person or any keyword. What are people talking? Are people talking negative about a particular keyword? Are people talking positive about a particular keyword? Or how is this behavior changing? How is this behavior changing over a period of time? So that is called a sentiment analysis. All right, that is called a sentiment analysis. So even though you are in a very beginning phases and you are deciding that, hey, what product should I build, or what kind of new product should we launch, or features should be launched, you figure out that these questions can be answered if we build some sort of sentiment analysis. And and therefore you will have to query a lot of data, you will have to churn a lot of data, and most of these sentiment analysis problem end up being big data problem, because we are talking about hundreds of terabytes of data or thousands of terabytes of data. Now, fourth is ad targeting. Ad targeting is advertisement targeting. This particular use case is for the companies like Google, InMobi, and Yahoo. They have lot of inventory of ads to be shown to the user, and there are a lot of real estate, meaning lot of people who are playing game, visiting websites, who need to be shown the ads. Now, matching the ad to a user's behavior is very important, because if an ad is relevant to the user will get benefited. In case the ad is not relevant to the user will get irritated. Okay. So the thin line between how good your ad targeting is differentiate between irritating and useful. That's the thin line. And therefore, the better ad targeting you build, the more successful you are. Okay. And when you do ad targeting, on one hand you have lakhs of 100,000 ads in your inventory, and hundreds of millions of users waiting for the ad. Okay, therefore ad targeting itself is a very complex business and makes up for a big data use case. Now, other than that, telecommunications companies are using big data for customer churn prevention. Based on understanding the user's behavior just before they left a telecommunication company, they are able to prevent the customer leaving them. And these are only few like 0.001% use cases of big data, but there are there are thousands of more and more use cases. Now, network performance optimization based on the users, based on where the density and other kind of analysis, fingerprinting the network behavior, network usage, these companies, telecommunication companies, come up with various kinds of plan of optimizing the networks. Third is calling data record analysis. Based on your calling behavior, they can do a lot of analysis and so on. All right. Now, government is also using a lot of big data for various kinds of use cases like fraud detection, security, and justice. Healthcare is also using big data for various kinds of gene sequencing, health information exchange, healthcare improvement, and drug safety. These are just few use cases. There are hundreds of use cases which are happening every day. Okay. So these use cases I have taken from Hadoop's use case website. Why? Because that is the easiest thing to do. All right. And uh, and this diagram shows that who is using how many instances of Hadoop, because Hadoop has become sort of alias to big data. Now, here are a set of myths which we need to counter before we move forward. First is big data always means data above and in range of terabyte, which we have already said. You will be clear to you. It's always about social media and doesn't apply to you. No, that's not the case. There are so many use cases. If you are ignoring the use cases, you are basically suffering a loss. It will replace enterprise data warehousing. Answer is no. Both will coexist parallelly. Reason being, EDWs are really fine tuned for structure and consistent data. Okay, but big data is tuned for handling large data and which cannot be done with that kind of consistency. It's just a big buzzword, no practical application. This is definitely a myth. Is a new concept? No. As I said, in 2002 itself, we were building lot of mm, ways of handling such kind of data. Will be the future? The answer is no. It is the present. Okay, it is the present. Is expensive? No, it's not expensive. All the tools, almost every tool in big data domain is open source. The only expensive part right now is the people who basically have there are only few people available in the industry, comparatively less people. It is only for data scientists or is a magic? Answer is no, it is not for data scientists. Okay, it is not only for data scientists. Whatever data scientists do, they generally make it available in the form of libraries. You can start using that. Okay, say for example, recommendation algorithm is just a library, just a command which you can start using. You can, you know, give a parameter that which algorithm you want to use, and then you can start using. So it's not only for data scientists. Okay, they gave an algorithm, but you need to know how to use it. We have got enough hardware. I heard it a couple of times. We have got enough hardware. We don't need anymore. So what's happening is lots of companies are trying to sell various organizations more and more hardware, but that's not required. That was required when we talked about vertical scaling. That was before Hadoop came along. Most of these distributed computing systems have been designed bottom up, thinking of commodity hardware. The commodity hardware as in the the PCs which are available in general. So most of the big data solutions can run on the existing architecture you have, so you don't need to buy a new hardware. We will build it when we need it. That is the general answer uh, we get. That is one thing which I want to say. You cannot at later point of time when you realize, oh, let's give our users some sort of recommendation engine. You cannot do it if you have not recorded their behavior, and you will not record the behavior if you don't have a data platform which is sufficiently available, which has a sufficient amount of space available in it. Therefore, you cannot build it when you need it. It'll take a considerable amount of time. So you should start doing it right away. You should start having a big data platform on which you can give the developers a peace of mind of starting to store anything. Big data is all about Hadoop. No, big data is not only about Hadoop. Okay, Hadoop is just one application. Hadoop is just one solution for big data. Okay, so the answer to the first point is, even though your data is small, okay, then also it might become the big data. As we talked in the first, second, third slide, even though your data has lower volume, by virtue of velocity or variety, your problem might be of big data. Okay, so I think I missed explaining what is vertical scaling and horizontal scaling. Okay, so let me give a good example. You have a cart. Okay, you have a cart in which you have bullock cart. There is one bull pulling the cart, and you're carrying 1 ton of weight. Tomorrow you want to carry more weight, and your one bull is not able to carry that. Either there are two things you could do now. You sell this bull, buy a bigger bull, or buy an elephant to pull the the cart. Or you can add two bulls in your cart so that you are able to do that. Okay? So the first one, where you sell the bull and buy an elephant to pull the cart, is called vertical scaling. While putting two bulls to pull a cart is called horizontal scaling. All right? So lots of people say that will be an okay. So how does this analogy relate to us? If you had one computer handling the user load, and if you are not able to handle that user load, you start increasing RAM, hard disk, or CPU, or network card. Okay, you start increasing all of the bandwidth. You throw away your old computer and buy a bigger one. That is called vertical scaling. If you add one more computer and start distributing load between the two, that is called horizontal scaling. All right. Big data will be the future. Basically, lots of people keep on saying that big data will be the future. It is actually the present. All right. Yes, horizontal scaling is far more practical and beneficial and possible than the vertical scaling. Because tomorrow, instead of 1 ton, you had to carry 20 ton. Now you cannot get an elephant of 10 times size, or you cannot wait for dinosaur to be created, right? And the same case in the programming. After after a point of time, we realize that the CPU is not growing faster beyond a point of time. The RAM is not growing faster suddenly. So we cannot wait. right? Therefore, horizontal scaling is the only solution, cost wise, as well as is only the possibility when your data is used, right? How do we decide which one should we go for? The answer is back of the calculation. Okay, back of the envelope calculation. You should be able to decide just based on a bit of computing that if this much data is being handled by this processor, what is our bottleneck? Can that bottleneck be resolved by vertically upscaling, or is it impossible to scale vertically? So you need to understand your problem upfront before you decide to go for vertical scaling and horizontal scaling. Say for example, if your CPU is bottleneck, okay, and you realize that we are really using a old one, 330 megahertz, which is running on say 20% 20% is on 20% usage. So if we increase the CPU to 1 gigahertz, we will have a benefit. And we are not foreseeing 10x kind of a load on our system. In those cases, you might be very happy to just upgrade your CPU. But in case you are foreseeing a growth pattern which will lead to an impossibility, then you need to think about horizontal scaling. Anamitra's answer is the best thing seems to do use is both scaling together. The good part about horizontal scaling is that it doesn't matter whether you do a vertical scaling or not. Okay. Vertical scaling is is the laziest option at any point of time. But once you have solved the horizontal scaling problem for two machines, that will be the same for 10 machines also. Okay. So 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 once you have solved your distributed computing problem for two machines or three machines, adding fourth machine should not be a problem. Okay. So therefore, the first, I mean, in most of the cases, horizontal scaling is a far better option. All right. So this is a graph, this is a chart which shows the salary distributions and everything. In very simple words, the based on the analysis of the data which is available in the market, the job scenario is very good in case of Hadoop, as well as the salaries are pretty high. All right. So before we get into anything, so are we convinced that big data need to be handled, right? There's a lot of data generated. There are a lot of use cases which you could do on top of the data, and hence a lot of companies will require a architecture which can solve their problems. So to solve such kind of needs, people realize that it's not possible with existing systems. All right. So for example, dog cutting was trying to build another search engine in his personal time, and that's when he realized that the main problem starts with storage, and therefore the usual storage is not of any use. And that's when a paper published by Google called Google File System came into use. He looked at he basically implemented Google File System for Hadoop distributed file system, and that solved the problem of storage. Okay. Afterwards, the other paper by Google called MapReduce was also he also implemented for computing on multiple hardware. So basically, is Hadoop is an umbrella term containing multiple distributed computing systems. It all started with two things. First is storage, or you can say it started with a file system and a compute engine. A file system is a place where you can store the data, and this file system was distributed file system. And the compute engine is something which can process your queries, which can process your questions, which can process your logic. Okay, so when you say select star from something, that is computing. Okay, and the data when you are storing into the system, insert into this, when you're putting the data into the database, that is storage. Okay, so what I'm trying to say is that it all started with a file system, distributed file system, and a distributed compute engine, and they basically implemented it for their search engine project. But soon enough, they made it open source so that everybody can use it. And afterwards, lots and lots of people started using it, and lots of similar systems started coming in, which complemented Hadoop, which complemented the Google the file system and the compute engine. Okay, so all of those became the part of the umbrella called Hadoop. As of today, Hadoop umbrella has close to 15 projects. Okay, all of them solve the same problem, the distributed computing problem. They they do it reliably and give it a do it scalably. Okay, so basically Hadoop is a suite of components which are reliable and scalable and for distributed computing. Yeah, umbrella as in it's a suite of components. It's not only map reduce uh, and the file system. It also has multiple other components under the umbrella. Okay, now so in general way, this is the whole architecture of Hadoop. The first and foremost is the file system. Just like you have your hard disk, you have, when you open Windows, you have C colon, D colon, that is file system. So they implemented a new file system on top of all of this so that multiple computers can be utilized. So first is file system, and then there are other components, which basically all of them depend on the file system. All right. Now, question is, why do we require a new file system? And the question is, why? What is so special about this? Okay. Now, we'll take a break a little later. Now, before I move forward, let me ask you this: if you had to build an storage system which can store 100 terabyte data, okay, how will you build such kind of storage system? Or if you have 100 terabyte of data, how would you store it? Imagine the real implication. Imagine that you live in a society, in a neighborhood, and all of your neighbors said that we want to build a common repository of movies or common repository of videos for this neighborhood, and you are responsible for it. How would you do it? How would you, your estimated storage is 100 terabyte, and how would you build such kind of storage? Any answers will be, any answers would be great. Just any answers. Or we can do one thing. We can take a 10 minutes break. Okay. So we'll just take a 10 minutes break and we will meet at 10:04. All right. So think about your solution and try to think about how will you build the hardware for it, how will you connect it, and what are the challenges going to be in your architecture. Okay, let's take a break for 10 minutes and come back at 10:04. I'll send the PPT to you, George, all of you via email, and those who are our student who have already signed up, this whole PPT will anyway be available in the learning management system. All right, bye bye, have a good day. We'll meet after 10 minutes. Okay, so all right, so let me let me read out your answers. Is everybody in? Should we start? All right. So, all right. So there are few answers I've got, really interesting ones. Group movies and store each group on different machines. Good, good. Break movies into parts and store on all the machines in the group. Excellent. Very excellent. That was Julie, and before that was Seema. All right. And Himanshu says that we can network together multiple computers, essentially summing their RAM together to get the total storage and performance. But here we are, Himanshu, that's a good answer. But instead of summing up RAM, we are trying to sum up the hard disk. Okay. Getting 100 terabyte RAM is a big deal, very, very big deal. Nakul says by using cloud storage. Nakul, think about if you had to build the cloud storage. You think about like an engineer that hey, I have to build this kind of cloud storage. What is it that I'm going to do? But good point. Anamitra says have Oracle RAC server pool in the storage. Okay. And for accessing continuing the answer of Oracle RAC server, for accessing the web server will ask for the data from the storage server depending on the request from different users. Okay. And I don't know what is you're talking about. I think you're talking about there will be multiple web servers if number of users are really more, and that cannot be handled by one server. All right. All right. The web server need to be load balanced. Okay. Okay. So that is one answer. Good. Good. And Seema is continuing her answer of group the movies and divide them by multiple computers, and then have a central file system that tells where to go. Very good. Very good. So Seema told two parts. One, first distribute the movies and then have an index which can tell you. Very good. Oracle with Lucene for search. That was Ranjit. Very great answers. Thanks to all. Now, most of us have given this as the answer. So, a, a way is specifically, I'm talking about SEMA, for example. Here, here, what we are saying is you buy 100 hard disks, okay? 1 terabyte of hard disk because we were trying to build is 100 terabyte of data, all right? So this is one of the solutions which we used to build earlier actually, that buy lot of hard disk, 1 terabyte hard disk, and put these hard disks onto multiple computers and connect these computers to make a network. And now these hard disks will be available to all the computers in the network. And just make sure that you map them to a central system. Mount these hard disks onto a single folder so that when the user opens that folder, he sees drive 1, drive 2, drive 3, drive 4, up to drive 100 under that folder. Okay. So basically we mounted drive 1 under a folder called drive 1 and so on. All right. So this is one of the solutions which we used to build as part of building a network attached storage or storage area network, or we generally used to call it network file system. Now, so Devik says Oracle also has options like advanced compression partitioning, which could be applied. Good point, right? Now, if you have, all right, so let me read Vidya's answer. If you have 101 terabyte capacity machines and use Hadoop distributed file system. Yeah. So basically, Vidya, that's the point I'm trying to drive. So I will not, I mean, basically, that's the answer trying to take. Before that, I want to discuss what are the challenges with this kind of approach. So this was the approach which we all took whenever we had to store humongous data. But there were a lot of challenges in this approach. So can you highlight some of the challenges? And note that on each drive, we can put a RAID kind of a backup so that the backup of drive 1 is on the same machine. Similarly, backup of drive 2 is on the same machine, and so on. So that in case drive gets corrupted, there is a backup of that one. So now, what are the problems do you see with this approach? So Seema's point is, if the problem I see with this approach is that if the popular movie is on one server, there'll be a lot of stress on that system. Very, very good point. Very good point. So we generally call that as availability. Good, great. Now, maintaining these devices, that is Himanshu. Excellent point. So, managing these devices because hard disks keep getting corrupted all the time. Okay. On an average, a normal hard disk gets corrupted at least once in 3 years or once in 2 years. That's the average. So, if you have thousands of hard disks, there are chances that every day you get one corrupted hard disk. Sushant says network failure. Yes, in case there is a network failure, the cable that is connecting drive 1 to the router, if that cable becomes faulty, there are mices in the data center and there are lots of other reasons of a failure of a network. Now, drive 1 becomes unavailable and all the movies we have put on drive 1 are lost. Very good point, Sushant. Searching will be a problem. That is Abhinav. Good. In case we have to look for data as other people are also saying, then it is going to be difficult. What is lame access method? Sushant? Delayed response. Yes. One device fail, network goes off. Those were Himanshu's answer. Those are the problems which we are expecting. Yes. Yes, Anamitra's point is, what if one node on which we have mounted all of this goes down? Then all of these drives are available. Very good point. Meaning, this index server which we have built, what if it goes down? Okay. So yes. So backup is anyway. Megha's point is the backup should be connected or on all systems. Yeah. So what we did was the way we always build the backup traditionally is we build a backup of hard disk on the same machine that prevents us, that saves us from the hard disk failure, but that doesn't save us from network failure. Yes, Avinash says if many access the same server, then it's a problem. Yes, very good point. Vidya's point is data could be lost, speed could be problem. We need to know which data is stored where. Excellent, Vidya. Very good. Excellent points. Okay, Himanshu says the searching will not be problem, but in this architecture, searching is but can be solved. Okay, that can be solved. That's what you're trying to say probably. Now, Julie's point is so each piece will need to be on more than one drive so it can recover for the lost piece. Excellent, very good. So, in Julie's answer, what she was suggesting is that divide the pieces onto the group of data. So, that's where we will take the discussion towards. So, you are just one step ahead, Julie. All right. If If we build a search method which might not fetch relevant data, that was like point we made earlier for one movie maybe 100 terabyte need to be searched in worst case scenario. Yes, that was Sushant. Good. All right. All right. So Himanshu, I'll repeat Julie's point later. Okay, because that's where we are going to anyway. All right. So you have given a wonderful answers. Probably you have covered almost all answers. Great. Now here are your basically the problems which I foresee, and you have already told them. What about failovers and backups? Okay, what if one machine goes down, one hard disk goes down, network goes down? Still, are we able to access a particular file? How would you distribute the data uniformly? What if basically if we are dividing the movies by alphabetically, there are high chances that one node containing all the movies starting with A is overloaded, but the node which contain movies starting with Q may be completely empty, right? So, is this the best value for money? Is this the best value of resources? You might have already so many data servers available. Couldn't you use those? You might be having hundreds of five smaller hard disks, but you'll say that in case we increase more hard disks, then there are more chances of failures and more problems, and therefore there are manageability headaches, and therefore we want to buy the biggest hard disks possible in the biggest hard disks available in the market, right? So you are not really utilizing, you are not really economical. What about increasing accessibility? That was the first point. Probably Seema raised that, and one of you also raised that point, Avinash, I think. And what if there is a new movie that came in this Friday, and all of us want to watch the same movie? In that case, that particular machine or that particular hard disk is get hit really badly, and at the end of it, it will choke, or maybe the machine shuts down, all right, or it gets corrupted, or it might get hanged. So in essence, it's not solving our problem. Okay, it's not solving our problem. Next is scaling out. Today today we had the need of 100 terabyte. Tomorrow we afforded some more money, and then we put 110 terabytes, and then we kept on adding more and more hardware every month. So this scaling out, meaning not scale up. Scale up is vertically scaling, scaling out is horizontally scaling. So this scaling out is possible or not. If we had this kind of architecture where we had movies, we had some scheme where we had devised that all the movies starting with A are here, B are here, C are here, so that may not be fairly scalable. You may not be able to scale out. So therefore, so these are the few challenges I see. So what is the solution then? The solution is to use a distributed file system such as Hadoop distributed file system. Okay. So and this is not something very uncommon. This is very, very, very common scenarios. All right. And here, that when we talk about distributing data uniformly, it also means that there could be a scenario where you are not able to fit 80 GB hard disks because there are only 79 GB available on one machine. Okay. So if you have a Blu-ray and you want to add that to one of the nodes and it only has 79 GB available, you will not be able to fit your movie over there. So that might lead to a bad distribution of the data. So, all right. So effectively, we use something called distributed file system. Okay. So is everybody convinced that we require some other solution? Is everybody convinced about the challenges? Himanshu? Yes. Anamitra is having a good point. So here the problem seems to fall under big data domain only because of the volume. Yes, as well as other is the you can say the velocity. Velocity will arise only in those cases when there are lots of users coming in, meaning this portion. A new movie came in, all the requests are coming and hitting one server. Even though you are able to afford the volume, safely able to store a movie, still, by virtue of so many requests coming in, you may not be able to one machine may not be able to handle it, because if you look at the hard disk, the way hard disk has got a header. The way you had those step recorders where the cassette used to move and there used to be a header which used to read the data from the cassette. In the similar way, there the cassette used to move, the strip used to move. Here the header moves radially. Header keeps on moving onto various tracks on the hard disk. Now, header is a physical device. So every time you ask hard disk, the header going to jump at that location, take a scoop and give the data to you. But if there are multiple people asking the same hard disk and the same header, the single alone header is scooping the data, then this hard disk, the header that header, the single header which reads from the hard disk is the bottleneck, right? So so it's not only the volume, it's also the velocity which comes into play here. Yes. So Anamitra's point is again, it's about scaling out. If you bring down 100 terabytes to say 50 terabyte, are we able to take out some of the hard disk from here and utilize it somewhere else? Yeah. Okay. So Anamitra's again point is, can we solve velocity problem velocity problem using CDN? Yes, definitely. But before, CDN is content delivery network. So many companies provide a way to deliver your content at a really fast pace. For example, take a case of Amazon CDN. Take a case of your website. You have just launched it. Your images are there on the website. So what you want is these images to be delivered to all the to everyone who is coming to your website at a really fast pace. Now some of the companies like Amazon CDN, what they did was they did a lot of optimization physically, as well as giving a lot of thought onto how image or these these content can be delivered across the globe at a very fast pace. So they built something called content delivery networks, which we call CDN. All right. So yes, CDN can be used for fairly static data. If you have fairly static data, a CDN is a very good choice. But in this case, it may not be, because uploading something to a CDN is going to take time. As well as if we choose to tomorrow we choose to take it offline because we no longer need so much of demand, then it is going to cost you. So yes. Okay, good, good, good. So Anamitra works for Akamai. Okay, Akamai is also one of the very brilliant content delivery network. Okay, so don't feel bad about that. All right. Now, good. So Megha's question is, what if we want to extract sentiment of the users from their search for of movies? Can we collect those sentiments on same machines? Multiple tasking like sentiments or recommendation. Yes, yes. So for that, you will have to build a little bit of a web server or some sort of engine which can basically track all of this information and keep it somewhere. All right, great. So Himanshu's question is, why are we focusing on distributed file system? So the reason is that is the basis of whole big data architecture. All the systems store in their data, whether configuration or real data or whatever, importing in, importing out, everything, whether it's HBase or MapReduce, or everybody is actually going to store the data in Hadoop distributed file system. Therefore, it is important to understand what is distributed file system and when do you use it. All right, so moving on. Now, first of all, let's talk about what we had discussed. All right, so we had all these problems, and how does HDFS solves those problems? So to solve these problems, first of all, what HDFS did was they created something called name node and data node. All right, name node is single system, while there could be multiple data nodes in the network. Also, name node, data node, all of these are basically processes which listen on a particular port and they keep on running continuously on the machines. And all these systems communicate over TCP/IP and by connecting to a particular port. All right. So basically, Hadoop distributed file system comes up with this architecture where there is one node which is called name node and there are multiple nodes called data nodes. Now, name node is an index. Name node is an index which keeps bookkeeping, which does the bookkeeping of which file is where. Okay, what data is located where, how many data nodes are there, and so on. So name node does a lot of bookkeeping, and this information is called metadata. Metadata is essentially data over data. Metadata is the information of where is the data, right? Therefore we call it metadata. Now this name node basically keeps all the metadata in the RAM, and which is in the backend is saved in the disk. All right, we'll talk about why does it keep in the RAM. Mainly because when the user asks name node anything, it gives the data immediately rather than reading from the disk, just to make it far more efficient. So name node keeps the metadata in the RAM. Now, what is data node? Data node essentially is the the node which is going to store your data. There are multiple data nodes, so there are multiple hard disks. They are all being utilized to store your data. All right. So data node is supposed to have good enough hard disk, but not great doesn't need to have big RAM. All right. While name node is expected to have bigger RAM. So data nodes store actual data and name node store the main data. Now next step. There's something called blocks. So before storing the data as is on data node, each file is sliced into blocks. Okay, when we are storing data into data node, the files are broken into small blocks, each of size 128 MB. Earlier it was 64 MB, now it is smaller, of 128 MB. So each brick is of the fixed size except for the last brick of the file. So when we are storing the data, when we are storing say 1 GB of movie, we are going to break it into the brick of 128 MB. Break, we can call brick, block, piece, slice, or whatever you want to call it, chunk. Okay, so we we break the whole file into small blocks, and that solves a lot of problems. It helps you fitting the big file into small hard disks. Okay, it leaves less space in each hard disk, as I talked about that we had 79 GB space available, but we had 80 GB movie to be stored. Now the 79 GB will go empty. So to make the distributed usage or distribution of data really well, SDFS guys came up with this idea of breaking the big file into blocks. Other thing is, when we are scaling out, more data nodes coming in, we are balancing the data and so on, it optimizes the data transfer between the nodes. Only the small amount of data is transferred. All right. The reason, like, before the innovation started, before the whole construction industry started, people used to construct the houses with big stones. They will take the full big stone, put it in the wall, and then try to construct the house. But later point of time, as the civilization evolved, they figured out that it will be more efficient if we have something called a brick, so that we can construct really good structure. In the similar way, breaking the big file into blocks gives us the enormous amount of flexibility. All right. Now the next feature of HDFS is, so I'll take your questions just after this slide. All right, so bear with me. Now each block in the data node has got multiple copies. Okay, so now HDFS, other than breaking the file into blocks, also provides you with the ability of replicating each block. Meaning, when you put one block onto data node 1, it will get copied to other nodes as well. Okay, by default, it is copied 3 times. Okay, and this 3 is called the replication factor. So, by default, it has the replication factor of 3. In case, in case a data node goes down, the replication factor has come down to 2, and immediately name node will order one of the data node to start replicating data to another one. Start replicating the blocks which got lost because of machine 2 going down. Say machine 2 goes down, and all the blocks that got lost will have replication factor decreased by 1. Earlier they had 3 copies, now they have 2 copies, right? Now to balance that, to bring back the replication factor as 3, it will order other data nodes to start copying to newer nodes, and that will start balancing it. Okay, to bring back the replication factor to 3, and this process keeps on happening all the time without you ever knowing about it. If you once you are rolling, once you are, you know, have learned HDFS, take a look at HDFS log. you will realize that there's so much of movement that keeps on happening all the time with respect to replication. And this replication happens between the data node. Okay? They directly communicate with each other and start copying it. Now, now this replication factor is really important idea. You can, in case your movie is really important, now you can set that replication factor to more, which means that movie will be available on more number of nodes. Okay, that will add a lot of copies, and when people are accessing that particular movie, they have many places to go. All right, that distributes the load across the cluster. Now, in case your data is not that important, you can live without the data. Then, if you can live without the data, then you can decrease the replication factor to 2. But I would not recommend bringing the replication factor to 1. Why? Because even if one block of your file is lost, okay, and losing one block of file is a possibility. Had your file been stored on one machine, okay, the probability of losing your file was less as compared to if your file is broken into three pieces, into multiple pieces, and these pieces are stored onto five machines. So in case either of the five machines get lost, get corrupted, your file is lost if you have single replication factor. Therefore, you should keep that in mind, because we splitted the file, distributed it. The downside is in case any of the file, in case any of the machine fails, your file is gone. The probability of one machine failing out of five is higher than, I mean, mm, the probability of either either one machine failing is 5 times than saying that this particular machine will fail. Therefore, say there are four machines. Probability of one machine failing is 0.25, second failing is 0.25, and so on. Okay, which means the probability of either of these machine failing is actually 1 over a period of some time. Therefore, you should always have a replication factor. So also, when the replication is happening, no two copies are kept on the same node. Okay, in case there are two nodes and you try to guarantee the replication factor of 3, HDFS will give an error saying cannot store this file, replication factor cannot be achieved. All right, now let me try to answer your questions. There are so many questions. So all right, so Avinash's question is name node as bottleneck. I'll tackle it very quickly. Okay, so Anamitra is saying the similar solution is by Oracle block as well. Okay, let me also study that. I haven't gone into the details of Oracle RAC you talked about earlier. What about small files? If the size is 20 MB or less than 128 MB, is it better to store in HDFS or NAS? So it is no harm to keep that file into HDFS. Okay, because you get the reliability anyway. You have the replication factor and all. So if your file is smaller, there will be only a single block of it, which will be size lesser than 128 MB, and there is no harm in keeping it here. All right, and it doesn't make sense. First, if you have data located at two places, then it becomes too much of a hassle combining the two data. Now, so if we have to store movie, so every movie will have a name node. No, this is the common place for all. Okay, the common place for all. Every movie will have an entry in the name node saying my file name is this, data is going into data node 1, data node 2, data node 3. Okay. Now, who maintains that one node is out of sync? That is maintained collaboratively by each data node as well as name node. Name node keeps is the authoritative information, and each data node keeps on syncing and talking to it. Individual data nodes, that was Anamitra's question. Another question from Anamitra is that the individual data node, or okay, so I think I've answered this. What are the common reasons for data block failure? The common reason for the data block failure are, first of all, the network. Second, the data block, it could fail because of the hard disk. Most probably, first reason is network and then hard disk. Every hard disk fails once at least in 2 years. Or each individual machine has got some problem. Maybe there's a virus, it has got deleted the files, or operating system got corrupted, it can't respond to the individual request. Can there be more than one admin node? The answer is no. Okay, because I'll come back to this quickly. Wouldn't the networking between the machines become a bottleneck? How is the bottleneck addressed? Good. So let me answer this with this. So the kind of bottleneck we expect is this way, that ideally Ideally, the way we design systems is the user comes to name node, and then name node reads the data from data nodes and then gives back. But that's not the case. The design is like this. User comes to the name node and says, "Hey, can you give me this file?" And name node tells the user that, hey, go to this data node and you can get the file, and then this user will start reading directly from the data node. Similarly, the data between data nodes that gets copied is direct connection. Name node doesn't read from data node 1 and put it in data node 2. No, that is directly between name node 1 data node 1 and data node 2. Why? Because if name node starts reading and doing all the things, then name node will become the bottleneck, and name node cannot afford to become the bottleneck, right? And Arun's question is, wouldn't the networking between the machines become the bottleneck? How so? So between the machines, generally it is not a bottleneck. Okay. First, because we have broken down a file into blocks which are located across the cluster, when the user comes in, it'll be reading from all the data nodes, not from a particular data node or a particular name node, right? Therefore, that whole bandwidth is actually distributed. So, Sushant, I didn't get your question. Increase redundancy and furthermore increase the hardware requirement, again hampering the efficiency of architecture. Mm, you mean, I didn't get the question. Yeah. So probably you mean to say that when we replicated each block thrice, so we increased the redundancy, which means you would require more hardware and hence more load. So the answer is that when you needed redundancy anyway, right? No matter what system do you design, you would need the redundancy anyway. whether it's NFS, network file system, the system which we designed, okay, well, had lot of problems. So anyway, when we said we'll keep a backup, we too doubled it anyway. So it is okay to buy more machine than suffer a loss. Okay, as long as you are able to utilize all of them properly by using a proper architecture, it is okay. All right. So what if admin node fail? That's a very good question. I'll answer it in a minute. So next question everybody has is, what if the admin node fails? What if the admin node fails? Now, first, in case the admin node fails, nothing would work. Why? Because admin node is the first point of contact. Admin node is like the reception person where everybody comes and meets and they say that you can wait, and the data node is coming to meet you. So that kind of thing. Now, in case admin node or name node fails, then everything hampers, right? Therefore, there is a mechanism called backup name node as well as secondary name node. Secondary name node is older. I'll talk about backup name node. So the design of the whole ecosystem architecture is such that each data node updates two persons, name node and a backup name node. Okay, each data node is designed in a way that when it's informing that, hey, this data got corrupted or we have finished writing this data, it informs two places. Similarly, name node, any changes it does, it informs the backup name node, which means the ditto copy of name node is maintained parallelly as a backup, as a failover. In case name node goes down, we can bring the mirror of the name node, which is being maintained continuously. All right. So just like data node informs back name node that, hey, I'm finished writing the data. Similarly, uh, the data node informs the backup name node also that I am finished with the data, maintaining exact mirror of what we have a name node, which means that in case name node goes down, we have a failover ready to take a place, right? Is there a backup for, okay, so everybody has the same question. Okay, so Sushant's question is it possible that just one data block on a node fails? If yes, how is that possible? Or it is the only case where the whole node fails? Okay, so there are chances that one data node might get corrupted, okay, because of bad sectors in the disk, because of other aspects, because one particular file, because at the end of day each data block is actually a file being stored in the native file system. Okay, each data node is actually running some Windows, Linux or whatever, and the data node process is telling the computer that, hey, can you store this file in this particular folder, it keeps on storing. If that happens, then basically there is some sort of a redundant cyclic, what do you call it, the check which keeps on happening, okay, which keep on happening parallelly, CRC check we call them. Okay, so if the data node doesn't match the signature, the block does not match the signature of the data which was kept, that means the data node, that block has been corrupted and will be rejected by name node, and name node will inform data nodes to make another copy of that block, and which got corrupted, and that block will be removed from the data node. Okay, so that's how it happens. I mean, I have suffered exactly the same scenario on my server recently, where one of the blocks got corrupted for some reason. So I was observing it. it got replicated immediately afterwards. Do we keep a current backup of name node and failover to it? Yes. So Arun's, so everybody is having the same question. Is name node replicated or for single point of failure? Yes. So what happens if name node fails? Yes. We have answered probably. Okay. Sushant, Sushant's point is we are duplicating data. My point answer is that it is absolutely okay, Sushant, to have the duplicate data for two reasons. The devices fail, and second reason is that it makes accessibility more of your file. And disk as such, if you have a smaller disk, if you are not trying to vertically scale up, if you don't want 2 TB or 10 TB suddenly, it's the device is not that costly. You can buy two 500 GB drives and they'll be completely okay. All right. So Julie's point is when the name node fails, does the data node become the name node? So no, it doesn't follow that kind of a mechanism where primary secondary kind of mechanism. It's mostly it's mostly the master slave kind of architecture. So generally, in case of say MongoDB or Zookeeper, the distributed architecture is such that all the slaves, all the secondary servers nominate a leader, and that leader is one which basically is the entry point. Now in case the leader goes down, the nodes select another leader. This is not the case here. We don't have that kind of case here. The name node selection is done by the sysadmin, who basically install and sets up the process, and in case it goes down, there is a failover waiting for the name node, right? It doesn't happen the way the HA, we call it high availability, is not achieved so easily in this architecture. People are working on that kind of architecture as well, but HDFS seems to fit even without those kind of possibilities. What if before replication a block of a file gets corrupted? How soon the block files get replicated? Okay, so Megha's question is that say as soon as you wrote the block, within millisecond a second it got deleted even before you start replicating, right? There's a very much possibility, but I mean that's a really difficult scenario. But good news is that as soon as you start writing the block, the data node starts copying it to another one, and so on. That process starts happening immediately. Is it a manual activity to bring backup node up? No, it is not a manual activity. It can be done based on the DNS lookup as well as um, I mean I mean basically by default as of today it is fairly manual, and it's not automatic. Okay, bringing the backup, making the backup name node as the name node is a little bit of a manual as of today. So Devendra's question is that don't we have a load balancer and multiple name node to address all these center point failure and availability of the server from the name node? Not yet, not yet. Do primary name node and backup name node run parallelly? Yes, both of them keeps on running parallelly so that the backup is maintained. So Anamitra's question is, there is some doubt regarding NFS, network file system, and distributed file system. Are both same? If not, how are they different? So there is a big difference between network file system and distributed file system. Why? Because this was the network file system. Network file system in simple word is any file system made available over TCP port. When people are connecting to your machine over TCP protocol, they are able to read files from the system. That's what we used to call it, network file system daemon, a process. And using these kind of daemons, we were able to construct this kind of architecture. Now, I hope you understand the difference between NFS and a distributed file system. So, going back to the question where one block of the data node gets corrupted, does the data node keeps on checking if all its blocks are fine, or the name node checks if all the data node blocks are fine? So none of them actually does it. When the client driver reads the data from the data node, it'll get something called a signature of the block from the name node, and then after reading it, it can quickly check that. Okay. Also, there are multiple ways it can check. First one is the size of the block. If the size of the block is tampered, then it will say this is a wrong file. Similarly, similarly, the client can inform the name node that hey, this block is wrong, and therefore it needs to be replicated. So it's those ways it is done. Okay. Also, if master name node fails, the slave takes over. Does it make the new master, or the sysadmin makes the new master as of today? Yes. So there is a dedicated backup name node. Yes, that's right, Julie. So you generally have to keep running both the processes parallelly. Devendra's question is, data miss can happen, but that could be handled at application level by handling errors from HDFS. Data miss can happen, but that could be handled at application level by handling. Exactly. So even if you are not able to write the first copy of your block, you get an error. The client can get an error, and then it tries again based on your application logic. You're right. So yeah, that's partly what Mega was asking. Yeah. Devendra, you were saying something. Is there a reason? Is there any reason? Okay, Asutoshi's question is, does it means there are two name nodes? Yes, there are two name nodes. Sort of two name nodes. One is backup and other is a copy. Other is the main one. All right. Great. Oh, okay. Okay. All right. So I hope this is clear to all of you. Now moving on. Now moving on. Now, this is the process which basically depicts what happens when we write the data. So, client comes up. This is the ugliest diagram that could be drawn on name node and data node architecture. I mean, of course, it is not my diagram, but so this one basically shows that there are data nodes containing these blocks, small blocks spread over this. The replication is happening between data node to another data nodes. The client comes in and client is writing directly to data nodes. But before writing directly, so when the client comes in, it can write directly to the data nodes, one block here, one block there, and the replication keeps on happening. And name node keeps on doing various kinds of block operations on data nodes. It keeps on telling that, hey, block one needs to be replicated onto from data node to data node 2, data node 1 to data node 2, and so on. It keeps on doing that. Name the name node, all the metadata operations are redirected to the name node, which means if the client need to create a directory, so can somebody tell me, can somebody tell me quickly, if you have to create a directory, will you talk to data node or not? Just quick. No, you would not need to talk to data node, because thank you Mega, you are very right. So the answer is no. Why? Because directory is not the data. It is the just the information that this is how I have distributed my data. Directory is just sort of a big file name separated by slashes. Okay. So directory, the information about directory is stored on name node. Even the name of the file is stored on the name node. So if you have 0 bytes of file, it will not go, your client will not go to the data node to create that data. It will only have the information at name node level saying there is this file which is of 0 size and it has no blocks at all. Great. Now this is the anatomy of a file write. So HDFS client, so who is HDFS client? The command you are going to use, or the driver you are going to use for writing the data into HDFS. When you want to create a file, just like FTP or SCP or any other way, you say Hadoop, copy this file from my local file system to the distributed file system, and that Hadoop, the command line which you're using is your HDFS client. Now using that command, you say Hadoop create file over there at the distributed file system. Now it will take the file, it will first of all it will inform the name node, inform the name node that, hey, I want to upload this file, so please create the metadata, please make a note of the metadata, and also mark that I am starting to write the file, so that if somebody else comes to write the same file, you tell him that there is somebody else already working on it. All right. So the first information is maintained at name node. Now once that is done, then client goes to one of the data nodes. It opens something called file system data output stream, which basically is a stream which connects you to one of the data nodes. And this data node is supposed to be closer or on the same machine as the HDFS client. Okay. So we start copying the data from local to the data node. Okay. And once that finishes, parallelly a copy keeps on going, as and when we are writing, a copy starts going to another data node and another data node. For the 3 copies, for each packet we are writing, there are 2 copies also being maintained. And once that is done, then the client goes to the name node, says, hey, I'm done successfully writing the data, and therefore now you can allow the reads of this data. These are the, and in the, also when HDFS client went to name node telling, I have got 1 GB file and I want to store, what do you suggest? Name node tells, why don't you go to these data nodes, these are the block size, why don't you go and create these block size and store it, and once you are done with it, let me know. And once it was done, it informed name nodes that I am done with writing the data. You can say mark it complete. All right. That means that name node is ensuring the consistency of the file system. Name node is making sure no two person try to write to the same file. No two persons are creating the same file twice, and so on. All right. So this is the anatomy of file write. Let me also show you anatomy of file read before answering the questions. So now another HDFS client comes in, opens the distributed file system, the read stream you can think of, and then talks to the name node, and it tells you, hey, this particular file you're talking about, this file, which I'll say, give me a/b.txt or a/b.avi, and a name node will look up in the metadata and say, oh, this file is located on these data nodes, and this file has got these blocks, block 1, block 2, block 3, block 4. The total size of the file is this much. Block 1 is stored on data 1, data node 1, data node 2, data node 3. Block 2 is stored on data node 3, data node 4, data node 6, and so on. And this way, that information is given to HDFS client. Now, it is up to the client to read the data from data nodes from the appropriate folder, appropriate data node. And that keeps on going. All right. Now, all right. Now let me answer your question. This is probably easier. Now Himanshu's next question is, suppose there are n data nodes, then if we want to replicate it 3 times, then there will be, where will be these replications created? So if you have got n data nodes and say your file was located on n by 2 nodes, right? Now let me just draw something, a simple one. So you had, say, data node 1, okay, and data node 2. Is my notepad visible to all of you? Data node 2, and you had data node 3, right? It has block 1, and say the block 2 is on this, okay, and block 3. Now we were happy till this point. Now the moment we have the replication of 3, so which means block 1 will exist here as well as here, and block 2 will exist here as well as here. Block 3 will exist here as well as here. So all 3 data node have the 3 copies. Had it been, say, we add one more data node called 4. So some of the blocks will shift here, okay, making it look like balanced. Sounds good? And this keeps on happening based on multiple algorithms. Okay. Now, Megha's question is, can two users simultaneously write two different files on the same node? Yes, they can. All right. So if you are trying to write, say, there is one user A who is trying to write file1.txt, B file2.txt. Okay. So A will go to name node. Okay. So here they will go into the sequence to the name node, and then there is a data node parallel there. They both can open the socket. The both can open the socket to a data node. All right. and so on. I'm pretty bad at drawing, so they can both open the socket to data node and start writing to the data node. All right, but there will be a slight bit of sequential in between. It will not be absolutely parallel. The way querying the name node was sequential, not parallel. Similarly, when before starting to write on data node, figuring out which blocks to write and opening the socket connections will be a will be a sequential. Once the socket connections, the file write streams have been opened, those both the streams can work in parallel. But it, if you see on the drive level, the hard disk level, when you write, there is only a single header, and that's when there will be problem. But data node can have multiple drives. It is not mandatory that each data node has one drive. Data node can have multiple drives. Okay, we can configure in data node that these are the two folders where you can store your data. Okay, by default it only stores in one hard disk, but if you have multiple hard disk on each node, you can configure data node to have multiple folders. Okay, and in these scenarios, like when two people trying to write, it will write to different folders. All right, so it is very important to gauge the data to be handled so as to avoid situation of failing short of hardware. How much buffer do we keep? Okay, that's a very good question Sushant is having. So the general thumb rule we followed at InMobi or elsewhere is like this: the moment we consume 80%, or I mean, or 75%, ठीक है? So if we consumed 80% of space, okay, we leads to doubling the hardware. It's as simple as that. So that was one design we followed. The moment we start reaching to 75% of the disk space, we double the hardware. Or it is absolutely up to you. But you should have a clear thought on how is your data going to grow. But this clear thought in the beginning sounds great, but when you have hundreds of teams or maybe 10 teams or for more teams, then this prediction of the graph, prediction of growth goes haywire. You cannot predict. Therefore, the general thumb rule is the moment you have 75% full, you just replicate this data. You said two users cannot write the same file at the same time. How does admin node determine the same file? Is it based on, it is based on the file name. It is based on the file name, Abhinav. It's not based on a hash or any other thing, because you can write two different files with the same content and without any problems. Does it have to be different folders or can it be different file names in the, does it have to be different folders or can it can be different file names? Do we choose that was Seema's question. Yeah, when two people trying to write the same file, I said a slash b.txt. So these all three files are different. A slash b and a slash. So let's say, let me put it this way: a slash b1.txt and a1 slash b.txt. Just like normal file system. Okay, just like for normal file system. Do we choose data node to write our file or is it name node who assigns block files? Do we choose data node to write our file or is it name node who assigns block files to data nodes? So it is the name node which will tell the client that, hey, go to that particular data node and start writing. All right. See, in case you are trying to write to the data node, which is already basically it's the data node which guides you where to write your data. It's not, and also don't consider it like this, that name node will take the data from you and then write it onto the data node. No. Name node will tell you, hey, go to that data node number X and start writing your data there. Can we take out any one of the data node out of stack, or should we keep maintaining the minimum same number of data node always? Okay. So as a thumb rule, if you want a replication factor of 3, you got to have minimum 3 nodes, right? Otherwise, the replication number of 3 cannot be achieved, because having the replication of the block on the same node is something which by design is wrong. Okay. Therefore, having 3 is sort of a mandatory, although it can live without that also, but you have to keep your replication factor lower, and also it keeps on giving you warnings that it is trying to keep the data on the same machine. Okay. Although it's not that SDFS requires you to have 3 nodes minimum. No, it just keeps giving a sort of warning, okay, that the replication is happening on the same data node. And if you have say 10 data nodes, okay, and you were maintaining good enough replication nicely, and after a point of time you just removed, basically you don't require 10th node, you can remove the 10th node and wait for the replication to finish, and then you remove the ninth and keep on decreasing the capacity slowly. Don't decrease the capacity suddenly to half. Okay. Don't decrease the capacity suddenly to half. You should remove one node and wait for some time for the replication to finish, then remove another node and then wait for some time for the replication to finish. All right. So yeah, I was talking about the secondary name node, or secondary name node has been replaced with some mechanism of backup name node. Okay. In secondary name node, there was some faults in the design, such as to bring up secondary name node to life, it used to take a lot of time. Therefore, there was a design change, and some people designed something called a backup name node, and we I think discussed backup name node. Okay, how many? Okay, there are a few more slides. We are almost through. What is the benefit of maintaining the rack of data node when after all everything is handled by single name node, right? So see, okay, that was Sushant, the name node is just maintaining the metadata, the actual content of say you have 1 GB of memory, 1 GB of movie. So the content, the actual movie is going to get stored in data nodes, while only the information such as the name of the file, the size of the file, etc., is going to get stored in name node. So, so uh, Gina Reddy's question is: does it support write multiple or read multiple? It support a single write, but it supports multiple reads, which means there could be multiple readers at the same time, but there could not be multiple writers or reader writers combined. Readers have to wait till the write finishes. Okay, so the metadata on name node is list of files, list of blocks for each file, list of data node for each blocks, and then file attributes such as access time, replication time, and file size. Okay, and also the directory name, file name, directory name. Okay, and most of the metadata is in the memory, which is paged onto the disk, which means in case the system goes down, there is always a copy. Okay. Sushant says that a rack is how I understand is clubbing multiple data node processed by one switch later controlled on the same data node. So, okay. So let me clarify here. So when you have multiple computers, so what how do you generally construct a network? Okay. How do you generally construct a network? So how do you do is that you first create take say 20 computers, put it in one Almira, and then connect all of them to a hub. Okay, generally these Almiras are called rack, and these racks come up with inbuilt hub in them. And once you connect all of these into that hub is connected to a router. Okay, and the router is connected to other routers, and that way bridging all the data centers. All right, now Now, in case, and this name node doesn't need to be on the same rack or same data center, it could be somewhere else. Okay, it could be somewhere else altogether. Routers is connected by switches and whatnot. A rack is how I understand clubbing data nodes processed by one switch later controlled by on one name node. Why not keep all data nodes floating directly under name node and not group it? Any benefit? So okay, that was Sushant's question. Now Sushant, okay, let me understand it. So what he's saying is, so this architecture where we have shown this diagram here, physically it looks like these are this way connected. No. Okay, these are absolutely floating around, as you are rightly suspecting. They keep floating around because there is something called network topology, and there is some, and these are simply the processes running in the network. They need not to be in in this way. Okay, because a network is a network. Okay, tomorrow you have HDFS running happy, but tomorrow you might run few more processes parallelly. If you look at our cloud labs, there are more than what you see here, more than HDFS actually. Okay, so the topology of the network is not generally driven by these kind of services, because there could be multiple such services. Okay, so Jinath Reddy's question is backup name node or secondary name node are same or no? Okay, so these were two different designs. There was something called secondary name node earlier, where the transaction log was made available. A transaction log record file creation, file deletion, and so on. And periodically, the metadata would be copied onto secondary name node, which means you had metadata on secondary name node, which was little older, but transaction logs were available immediately. Okay. Now, the problem with this architecture was whenever your name node goes down, you will have a lot of time you will take a lot of time to bring the metadata by using transaction log to the current state. Okay, and therefore the design was flawed. Instead, people designed something called backup name node. which basically keeps a mirror of exact mirror ready to take the position. Okay, so these were the two kinds of architectures. All right, now that was what we discussed about all of the things regarding Hadoop distributed file system. Hope I am able to answer. Did I miss anybody's question? There is one question I remember in the beginning of session which I have not answered. All right, so moving on, we have 6 more minutes. Now, on top of HDFS file system, there are things like importing data from unstructured sources to HDFS. Unstructured as in your data could be log file, your data could be binary files, your data could be images, videos, and whatnot. And structured data such as relational data. To move unstructured data, you have a tool called Flume. To move the structured data from, say, MySQL or MS SQL onto Hadoop distributed file system, you use Scoop. Now, most of you will say that why do we need these kind of systems? Why can't I write my own and do it straight away? Basically, Scoop has gone to further far more steps where there are multiple processes that happen and each data node connects to your, it makes each data node talk to your structured data and make a copy of it. So Scoop as well as Flume both are extremely efficient systems for importing and exporting data. Now on top of HDFS, there is something called yarn, the compute engine. Okay, what does this compute engine does? Whenever you want to do some computation, say you want to sort the data, you want to order the data, basically you could do this on individual nodes separately. Okay, all the data nodes can be utilized to do the sorting and bring back the information on a central node. So effectively distributing the computing onto multiple computers is the role of yarn. Okay, now to actually break down the problem into this kind of statement where we are sending the code to the data, there are two basic paradigm. One is MapReduce, and there are new softwares like Spark, which basically run on top of Yarn and HDFS to give you a great interface for doing any kind of computing. All right. So MapReduce and Spark are two examples of systems which run on top of Yarn. Yarn is the basic yet another resource negotiator, whereby you programmatically tell Yarn that, hey, I want to run this code on all these machines, and so on. Now, there is something called HBase. HBase is designed, HDFS is designed for just dumping the files, like your C colon, D colon, or your any Unix file system. HBase is designed for really high rate of record wise manipulation, just like another database. So HBase is a data store which is in the form of key and values. Okay, and such kind of systems actually run. HBase is a NoSQL database. What does it mean? It runs on multitude of computers parallelly. Basically, you can define that HBase should run on these computers. But HBase would be storing its data on HDFS. And whenever you do the computation of HBase, you would be using Yarn for the computation. Okay. Now you have something called Hive. Okay, you have something called Hive. Hive is essentially an SQL interface for your computation, because in case of MapReduce you have to break down your problems into maps and reduces. That's not great and efficient manner from the perspective of the developer. So people came up with the idea that we can put our existing SQL such that it can convert every query into MapReduce logic. So Hive does that for you. If you have to run a query, if you want to query a data lying in HDFS or HBase, you use Hive. If you have similar to Hive, so people designed a piglet specifically for distributed computing. And then you have Mahout. Mahout is a library of algorithms such as clustering and machine learning. And whenever you have a big project, it will involve multiple of such tools. You will have import, you will have churning of data using MapReduce, you will have queries, and to tie all of these together, there is something called Uzi, which is basically like your Apache Ant or Maven or Make. Basically it combines all of these processes together so that it gives you the result. All right, so that's pretty much it. Now we have something called Cloud Labs. Those people who have signed up, they would be knowing a bit. Now basically we have set up a cluster for all of you where you can log in from office or home and connect and start working on that. Cloud Labs is essentially a sort of a cluster. It has a name node, it has data nodes, it has all of these tools which we have discussed. So as and when we will be working, you will log in there. The information about Cloud Labs is available in the installation document under session 1. If you have my under my courses, you will have, so under your courses, under my courses, say you have this, and in this you will see you can basically finish the quiz after the session, take a look at the presentation, and for all of those who want the presentation right now, let me give it to you. Okay, I'm just sending to all. Okay, but nevertheless I'll be sending the video as well as this presentation in the email also, so those who have signed up, they can see this, and the recorded session will appear here. Right now it's the old one. Similarly, you have regular expression presentation as well as regular expression session. Now, because this regular expression will be required during the class, take a look at the installation instruction. You will see how to connect to the cloud, what is the login password, and then you can connect there. All right. So you can have a look at the the cloud lab. So Cloud Lab has multiple interfaces. One is Ambari, other is Hue, and other one is SSH. So you can connect from either way and have a look at the system. All right. So here you can see that HDFS, Yarn, MapReduce, HBase, Hive, all of these services are running. And the disk space, this is a cumulative disk space, is 51% consumed. Okay. Now the data node, all four of four are live, and so on. Okay, there are four data nodes, one name node, secondary name node is also up, and so on. All right, so right now the total number of nodes we have four, and whenever we see that they are not sufficient, more people are joining in, we keep on adding data nodes. All right, now you have HBase master and the reason server, everything is there. So this shows you the health, and then to interact you can go to 8000 port and then log in. All right, here you can see HDFS. Okay, create your own folder, separate folder, and the password will not be shared with you. With password is available in the installation document. So here you create your own folder and start working on it. And these are other people's folder. I mean, you will soon receive your separate login also. Okay. Now That was about Cloud Labs. So I hope you understand, as well as you can do an SSH onto the server. This is okay. You can SSH onto the server. All right. So, so that is what it is. And so finish your quiz, go through the installation document. It is absolutely up to you to install the virtual machine, Hortonworks. We basically go with the Hortonworks virtual machine rather than Cloudera, and go through the presentation again and finish the quiz. Okay, and those who have not, who want to sign up, who want to complete rest of the 10 sessions, can go to the website and then and then enroll. Okay, you can go to the website and enroll. Okay, okay, so you can enroll from there, and you can continue the rest of the sessions from tomorrow onwards. All right. All right, so if you have any questions, you can reach out to this phone number or reach out to us at this, mm, reach us at No Big Data, and feel free to connect with me. All right. Also, if you have more questions, you can come to our forum, www.nobigdata/forum, where lots of people keep on asking questions and we keep on answering it. Okay, even if you are not signing up, you can still be part of our forum. Okay, even if you are not enrolling for the course, still you can be part of our forum. The rest of the sessions will be at the same time, Julie, and I'm running 6 minutes late. All right. Yes, you'll all get the slides. I'll send the email to all of you. All right. Thank you. I'm flattered, Devendra, that you found the session lovely and wonderfully presented. I'm pretty happy. Great. I too look forward to this kind of discussion. I find a really, really good set of questions from you. And yeah, really enjoyed the session. Thank you, Seema. Please give the feedback at the end of session. It will be great. We want to keep improving our sessions. Every new session is better than the previous one. We keep on working on that. So please give the feedback which you will see at the end of the session. All right. And I look forward to all of you to be part of the sessions. And I hope, in case you are not able to enroll to the sessions, please be active on our forum. Our students or we all can keep on answering the questions. Thank you, Anamitra. Happy that you found the session very informative. All right. So there was somebody's question regarding. I will actually look at that question. This was in the beginning. I think I had skipped that question, but with the hope that I'll be able to answer it by the end. All right, all right. So we struggle really hard. We try our best to basically make our explanations really easy, okay, and tolerable. So Megha, the link will be sending you separately. Before half an hour before the session starts, we will be sending you the link. All right. All right. It was a great session.